Okay, ready to go?
When I was born that way.
You were born unready.
I was just born.
You were. That's where the time started. Yes. Okay. Today we are continuing our quest, our journey through Intel's various generations of CPUs. But I was thinking that we could do a little bit of a speed up because we don't want to do 100 episodes, although we probably could. And my goal for today was to try to go through the next 5 to 6, let's say, generations of Intel CPUs. We finished the last episode in our Intel series with Pentium IVs, and we talked about the press cuts and Pentium Ds. So our goal today is to start with the core architecture generation 1 to, let's say, 5 to 6. That's it. With that being said, welcome to the new episode of That IT Show. Let's roll the intro and start discussing. Okie dokie. Why are you sitting like somebody is pointing a gun at your face?
I'm trying to come up with a good start for the episode because basically your introduction was boring.
Thank you.
And I wanted to just say that let's just say that what we are trying to accomplish today is we are going to try to talk about when Intel finally decided that having one core is not enough and that they have to have an actual multi-core processor. Mm-hmm. Pentium D is not that thing.
Okay.
So they decided that they're going to be working and create something out of Pentium Pro. And they're going to be trying to create something that was multi-core. Mm-hmm. And I think that we should end with the latest generation that was, let's say, generic multi-core architecture that didn't have different cores. So heterogeneous cores should be the cutoff point for this episode.
That's like generation 12 or something like that.
I think it's 11, but yes, the last one was 11.
Okay, sounds good.
Because the what Intel did is they got stuck in a rut once again, and
not with the first few generations.
Yes,
though.
but they innovated. The innovation was working good.
Up to a point.
Up to a point, but no, it was good, working good at the start for them, and then they did what Intel usually does best, and they got stuck. Mm-hmm. They decided that just creating additional cores, the additional ramping up the core density, ramping up the transistor count is just simply enough to make processors that are, I would say, good, but that fit the market. And I think this is one of the main reasons why we got stuck for a few years with laptops that were less than ideal for a laptop.
We already had that in previous generations as well, but yeah, during the Intel Core phase, at least the 14 generations that came out before the next one that's going to come out supposedly later this year or next year, which is going to be a fundamental shift for Intel. Yeah, more than a few occasions of that happened. But I would still like to keep the format of talking about certain aspects of the architecture of every single one of these generations, because there are some important things to note there.
No, there are important things, but the thing is, looking into perspective, what I wanted to just point out is that I wouldn't say it was bothering me, but when I looked back to what the laptops were and what they could have been, if the shift in architecture came sooner rather than later, and there were no reasons not to do those, except for the basically business decision of Intel, because I guess this can only be described as a business decision. Trying to create a multi-core processor that has cores that are all identical is something that is a business decision, and I think that this is due to lack of courage to go a different route.
Okay, that's possible.
And the thing is that what I want to note is that while they were developing Pentiums, Pentium IVs, Pentium IIIs, and so on, they also had a different team that was developing Pentium Pros. This turned into a team that was developing Xeons, but they didn't have any alternative paths to mainstream Pentiums that they were creating. So the core architecture, and then after this, the however the naming was in a particular moment in time, because this is when the different changes in naming came. There were no alternatives. The Xeons were created for the business market, but they were kind of close to the same to the architecture that was on the desktop market. So what Pentium Pro was for the initial Pentium line, it was a completely different architecture. It was completely differently styled, it was completely differently designed, and I think that this was something that was lacking when Intel was developing the core. It just simply, the alternative wasn't there.
Okay. So let's start with the first one, which is Nehalem. I have vivid memories of the first generation of that. I spent an awful lot of time testing loads of motherboards of that era and the CPUs as well. And I would say that there were quite a few architectural firsts in that specific generation of the CPUs. Now it's been a while, so this was a generation that was introduced I don't know, 2000 whatever. 5, 6, whatever. It was quite a while ago. But I do remember some of the things that Nehalem brought, which were really important. I would actually note 2. Integrated memory controller, which AMD already had, and QPI, Quick Path Interconnect.
Yes, okay.
The reason why I'm singling these out, it's going to sound a little bit of selfish, but it's not my interest for that, is purely professional, is because some of the things that I learned over the course of the years when we were still doing the journalist thing back way then, specifically related to this generation, still is something that has a long-term effect on my professional development right now, because I published more than a few papers related to some of the technologies like that. It's a very interesting topic to look into from the perspective of what we do today.
Okay.
Because integrated memory controller, unlike what we used to have, which was memory controller on the Northbridge chip, is a way better method of accessing memory in terms of latency, speed, and everything else. No question about it. Later on, we also got the CPUs that had PCI Express controller direct on the CPU, which again is a better way than to have a Northbridge chip, whatnot.
And this basically ended up with the current processors on the ARM side that have integrated memory basically on the CPU itself.
Yeah, this is where the next generation of Intel is going as well, from the reports that we can find on the net and from.
But this is logical. This is just something that's going to happen, and this is going to be another set of surprised reporters that are suddenly going to realize, oh no, the newer generation of the laptops is unable to be upgraded with the memory. We don't know the reasoning behind this.
Yeah.
And this is breaking news right now. The reasoning is because in order to get the memory as close to the chip as possible, you can put it on the chip, but then you need to basically tear apart the chip in order to upgrade the memory. So there is no way to upgrade the memory once it's inside or right on the chip itself.
Think M1, M2, M3.
Yes, but we're still seeing different texts that are, or articles
surprised
that are acting surprised. They say, why is Apple not introducing a new generation that is going to be upgradable? No, they are not going to do this. Not in this particular shift in technology. If they want to do this, they need to create. They wouldn't have need to create a socket on the chip itself. So you would need to have a processor that is going to have a socket on it in order to accommodate additional memory.
Which is expensive.
And this is not going to happen due to thermals. The thermals is the only problem.
Yeah, basically the topic that we mentioned, I think, dozens of times over the course of the past year and a half since we started doing this podcast. So integrated memory controller, a logical next step is integrated memory. That's the correct design decision, however we may feel about it. The QPI is the second one. Again, this is very important for some of the topics that we are currently doing some research in, because the way in which processors interoperate, especially on the servers now, we're not necessarily talking on the desktops. over the QPI interface and the way in which we design systems nowadays. That way of designing things would be fundamentally different if we didn't have QPI. If we had what we had in the past, the bridge chips on the first Opteron generations and early Xeon chipsets as well, it would be a vastly different user experience in terms of the latency and what a lot of people are basically referring to quality of service, because quality of service over these sorts of interfaces that used to exist prior to QPI was a non-existent terminology. Think about it this way. If you have two CPUs, if they have banks of memory, if the consumer of that memory is larger than the amount of memory that you have on one of the CPUs, the process that is requesting memory access needs to have access to second CPU's memory as well, which takes a hell of a lot more time than to go to the banks of the first CPU. This is what the discussion about the SMP and NUMA and whatnot has brought to us, and all of that stems from the different design pattern, which included QPI interface. Also, if I remember correctly, as a side note, they had a turbo.
Yes, the turbo boost was available on this, and the hybrid threading became available once again.
Yes, yeah, all of a sudden they resurrected that one as well, because it wasn't present in some of the CPUs that happened in the meanwhile. They were quite a substantial shift, I think, these CPUs, when compared to the Prescotts and Pentium Ds. Actual real multi-core CPUs, they used to have, if I remember correct, they still had the shared cache, but they were real multi-core designs. That's very important. And the QPI and the integrated memory controller, those were quite a big quantum shifts when compared to the Pentiums IV and III and Pentium D and Prescotts and whatever you want to compare that to from the previous generations. And Intel was quite successful with these CPUs. They were very popular.
Okay, but let's get a few things out of the way before we do more on Nehalem. We need to talk about Conroe, and we need to talk about Penryn.
Okay.
Because they were shifts from NetBurst. Mm-hmm. So what happened is that Intel decided that they are going to be something that is going to change the market, and they needed something to change the technology.
Those were core to duos and quads?
Yes, these were the first ones that were basically trying to shift the attention away from having a single core. And this was the shift from NetBurst, because NetBurst was the main technology behind Intel's Pentium 4s for a long time. Mm-hmm. And then they decided that they needed to do something new. So they came with Conroe first, and then they were using Penryn. Mm-hmm. And the idea behind the Conroe and the Penryn was that they were trying to play with how the memory was used, so the memory access. The Nehalem is probably the result of that testing. Mm-hmm. And both Conroe and Penryn were different when it came to accessing the memory.
Okay.
They were trying to understand how the caching, when you have multi-core processor, how the caching should work. Mm-hmm. Because you need to take into account that when we say Intel just introduced multi-core, mm-hmm. it's not as simple as this. Nobody had all the numbers and all the ideas how this multi-core thing should work. Mm-hmm. So sharing memory, sharing caches, how the caches should be shared, what information should be in the cache, how did we end up with the 5-page access in the newest Pentium processors and so on. So different things that are normal today. Mm-hmm. How did we come to this? And Conroe and Penryn are not today. When we look at them today, they're not that interesting because they weren't.
They were very interesting back then.
Yes, but today they're not that interesting because we take for granted that all the processors should be multi-core. Hybrid threading is also presumed. I wouldn't say that.
But they're doing away with that.
Yes, they are going away from the hybrid threading, but it was presumed. But this was not a thing that was a thing way back then. Mm-hmm. The first and the most important thing was that they shifted from single core to multi-core. And then they try to understand how to make this multi-core thing run. and how to make the memory available to all the cores.
Yeah, Conroe, Penryn, and then Nehalem. That's the strategy that over time, if you want to look at from the history timeline. I remember when we were writing articles about that, a lot of people were saying that Penryn is just a die shrink of Conroe, which was far from true. Actually, it was quite a bit more advanced CPU, and you are exactly on the money by saying that what Intel learned from both of these processors ended up as Penryn, which was very successful CPU for them.
The thing is that the problem that they created for themselves is that they were using front-side bus.
Yep.
And the thing was that they couldn't figure out how to do the memory interconnect and everything else that is related to this. So they had a bottleneck that was a big problem. Mm-hmm. The other thing is that Conroe, unlike other chipsets that we have today, was completely missing the graphics part.
Yeah, that came about later.
Yes, yeah. And this is also one of the things that we take for granted.
Yeah, sure.
Now people say, okay, we have integrated graphics, but this was not the case way back then.
Yep.
Graphics was almost exclusively done as a discrete graphics card.
Yep.
And you had to get the card. Some of the cards, okay, we are talking about the time where some of the cards didn't even support 3D. Mm-hmm. So we still had 2D VGA cards, mm-hmm. which is also something that people don't understand how it actually was able to work. But you just had a card that wasn't able to do three-dimensional calculations in hardware. Mm-hmm. You just had to do it in software, so it made every 3D game basically a feast of technology because you had to do everything in software.
Mm-hmm. All good?
Oh, yes. Okay. So now that we have put the Conroe out of the way, let's talk about the Pentium. The Pentium was an upgrade to Conroe. Mm. It was better when it says the performance itself was better. It was cooler. Mm-hmm. Because it was basically
quite a bit more energy efficient.
Yes, and this is more or less because of the upgrade to the process. So the process itself was instead of 65, it was 45 nanometers. Yeah. So it was the smaller process size. So the processor was smaller and it was easier to do the energy efficiency stuff on it. So and it was slightly faster than the processor before that.
I would also put on the table one more thing, very, very briefly. When you compare those CPUs to Pentiums D, for example, or Prescott's, is just unimaginable difference in terms of the thermals, efficiency. Yes. And as an end result to that, because the cooling performance back then from the coolers was not as good as it is today, we have to keep that in mind. As a result of that, the overall efficiency and the speed of the CPUs of for example, Penryn compared to anything like Pentium D was just out of the world compared to it.
And the other thing was that also we need to talk about the technologies that we take exclusively for granted right now. Mm-hmm. Penryn introduced enhanced Intel speed step, mm-hmm. and also
one of the most important technologies still to this day.
And the SSE4.
Yeah, still.
So again. multimedia processing and high computational applications, basically, they finally realized that the processor that they're creating is not only going to be able to be used on the desktop, but also it was able to be used in the server market. At that particular point, they didn't have a Xeon processors, if I remember mm-hmm. correctly.
Yeah.
Xeons came somewhere about this, but it was not uncommon to see a server that was basically repackaged the desktop processors with better motherboards and with much better support for everything on the motherboard. But the thing was that the processor itself wasn't that different than what you had on the desktop. Yeah,
they started re-architecting the server CPUs way later in the cycle. That was nowhere near that. Yeah, you're completely on the money with that as well. Okay, next one is, believe it or not, it's Sandy Bridge.
Yes.
Which was, if I remember correctly, 2011, which is quite a bit of time passed since the Conroe, the Penryn, whatever. There were some mobile generations there as well, but let's forget about that. We are talking about the desktop CPUs mostly and a little bit about the servers. Sandy Bridge is something that's very important for a variety of different reasons. You're going to like this. If I remember correctly, yet again, Sandy Bridge was the first one with integrated graphics. Very important to this day because, again, there are people who don't need any 2D, 3D performance for games, whatnot, for business PCs, for laptops. They are not optimized for graphics performance, whatnot. Very important thing to notice that there are CPUs with basically the graphics chip on. You connect the HDMI cable or whatever to the motherboard and everybody is happy. The second one, which was quite big, was in line with SSE. From the previous generation, the Sandy Bridge brought on the AVX instructions. Very, yes. Very, very, very important. This is going to become a theme as the later generations of the CPUs come about, because to your point about servers, it's not only about that, it's about although it is largely in large part about the servers, it's also about the desktops and getting them a decent slice of upgrade in terms of the multimedia performance without redesigning the whole CPU or putting a graphics card on top of it and using too much of a die space for that. Because some of the instructions, like MMXs, for example, they were much more in line with the idea of multimedia. That's what they are. AVX is something that's completely different. It's about vector operations, which is fundamentally what graphics cards mostly do. And in scientific computation and whatnot, that's what that part of the market needs. So AVX offered quite a bit of more width in terms of the programmability that was needed for those markets.
Let me just stop you there for two things. First, I need to correct myself because I checked. Intel Xeon were introduced in 1998.
Yeah.
So before, but they weren't that prevalent when it came to servers, simply because they were much more expensive.
Yes.
Also, one more thing. Before we go and talk about Xeons, we talk about cores and everything else, we need to go back to Nehalem. But simply because to say that this was one of the most important steps when it came from the single core processor to the multi-core processors and so on. But also we should be mentioning Itanium.
Yeah, but
because Itanium was a side quest for Intel.
Yeah, that's a separate team doing something for Intel. I was actually thinking that we definitely need to do 1 or 2 episodes about Itanium because I don't think that it was as big of a flop technology-wise as it was presented.
I don't think that it was a flop. I think that what happened with Itanium, and I am going to ask Vedran to put an amazing video on Itanium from Retrobytes in the description. But the thing is that I want to just say that the thing that happened with Itaniums was that this was one of those times where Intel was basically creating something that would be normal for the 80s. They created the server-centric processor. They created it in a way that it was intended to be used for the processing in the
mission critical systems.
In mission critical system and in data centers, basically. And the thing that they wanted to do is that they wanted to create the something that is going to be used in parallel instruction computing. They even called it EPIC, explicitly parallel instruction computing. And the thing was that way back then, the problem wasn't that the market didn't exist. The problem is that the much larger market for the desktops existed.
Yep.
So the dedicated hardware for the servers was just not ripe to be on the market. At the same time, Xeons were coming to the market and the faster processors were coming to the market when it came to x86. So it meant that Itaniums were pretty stranded when it came to applications. And this is more or less the same thing that is right now happening with the ARM. You have the ARM processors that are completely capable of doing servers, but you don't have enough applications yet.
You do one if you use
I'd say
Linux.
Yet.
No. If you have Linux, you are covered very well.
Okay.
There are loads of data centers being built right now, and especially in the scientific community. I know I'm involved in some of those things that are using exclusively ARM CPUs, specifically the Huawei's of the world and whatnot, they have quite advanced architectures based on ARM with some stuff like 128 to 156 cores on a single die. So that's definitely happening. Not as fast as you might want, but or not as fast as it could because of the problems with the restrictions, sales restrictions of technology and whatnot, which has been in place for years now. But still, there are quite a few very advanced ARM-based CPUs that are being built specifically for the server and the cloud market, and I work with them on a daily basis. Some of the lower architectures of that, if you want to run Kubernetes and stuff on top of that, no problem. So for a lot of stuff that normal people use in the data center to host web applications or stuff like that, they're perfectly good servers. And later on, in the fight for that market, there is another player that's kind of emerging, based on the idea of open source design, which is RISC-V, and that's something that we're going to discuss.
Topic that we're going to talk about.
But this is where the market is now.
But when you mentioned the market that is right now emerging, I would just simply say that in a world where data centers more or less stopped billing you by the unit and started billing you by the power consumed, because this is what is happening right now, it makes awful lot of sense to create an ARM-based infrastructure, especially if you are doing something like, let's say, web hosting. A web hosting provider that is a small business can probably do 7 to 10 times more with the given amount of power in hosting if they are using ARM than if they are using Intel.
You're completely correct, and there are quite a few available already. You can search for that on Google. There are ARM-based virtual machines, instances in all of the clouds nowadays. You can use them, and they usually cost quite a bit less than the x86-based variants. And there are a couple of other markets where ARM is super interesting. I would just like to mention one of the experiences with that. There are loads of ARM CPUs, as you mentioned previously, and we mentioned multiple times. A lot of the stuff that's happening in the ARM ecosystem nowadays revolves integrated memory. That kind of gives you the pointer into the direction or which market might take heavily, might let's say buy heavily into the ARM architecture, which is exactly the topic that I'm currently investigating for my PhD research, which is high performance computing, especially applications that are memory bound. The reason being that, believe it or not, you can read this in one of my papers, memory performance of some of the applications on HPC. And memory is out of utmost importance in parallel applications. If you're using something like a Raspberry Pi, it can top the performance of Gen 8, Gen 9 HP processors if you have an application that is very memory bound. Which comparing Gen 9 HP server with 32 cores, that's consuming 400 watts of power, let's say, in the standard performance envelope, versus a Raspberry Pi which consumes 5 or 10 watts depending on the model. That's 1 to 40 or 1 to 80 difference. And this one is the ARMs are still faster because of the built-in memory.
And this is one of the reasons why you can get computers that were considered basically supercomputer material. I wouldn't say dirt cheap, but I would say cheaper than this. I just wanted to make a completely side note.
Side
note, because this is I don't know when this episode is going to be out, but right now it's the 1st of May, and there is a supercomputer for sale. It's called Cheyenne Supercomputer in Wyoming. They're selling it for right now the bid is at $51,000, which is a lot of money. But yes,
until you look what's in it.
But when you take a look at what's in it, you just need to look at these numbers. 4,032 dual socket units, comprising of 8,064 units of E5 2697 V4.
Yeah.
This is 18 core, 2.3 gigahertz base, first frequency turbo 3.6. That comes to a total of 145,155 cores.
Then
And each processor is using 145 watts of TDP. So this comes to something like 1.3 megawatts of power required to run this computer.
How much memory?
313 terabytes memory of DDR4 240.
And is it are they GPU enabled or are they just CPU?
They are just CPUs, as I can see, and they're configured as SGI ICE XA. So they also have integrated cooling. This is additional 14 units of cooling. So I didn't do the maths, but it should be something like 9 to 10 tons of equipment. So even given the amount of money that you need to pay for this, of $50,000, it's probably going to go up because 2 days are remaining for the auction. But I would say that you could recoup most of it if it just came to scrap metal.
I think we could buy that and sell that and make money.
Yes.
Easily.
313 terabytes of DDR4 is something that is costing more than the amount of for this entire computer.
If this was in Europe, this is from US.
Yes, US.
If this was sitting somewhere in Europe, I would actually go and talk to some people to buy that to make some money.
Yes, we would have a problem. Okay, the only
the
thing
shipping
is that,
and the taxes would kill us.
I think that you cannot just do the shipping. This is one of those jobs when you need to go on site, arrange for the operations, create an operations plan. You need to create an operations plan, how to lift the entire thing, and so on and so on.
Yeah.
But I wanted to say that people are getting rid of the old computers, not because the old computers are old. It's simply because they are energy inefficient.
Yep.
And what Intel was doing, and what Intel is doing right now, and ARM is doing right now, is they are shifting the idea of computing in a completely different direction.
Green computing.
It's not that it's green computing. I am all for green computing and not wasting energy and so on. But the idea is that you can have much more for less. You can reuse your old infrastructure and do a lot more if you just simply, because this is giving a computer away. $50,000 for 10 tons of computer, because the switches that they're using
extreme network
switches, and there is something like
40 switches. No, more. It's more. I remember that you mentioned some insane number.
So the switches are extreme networks, and the switches are 10 units of switches, 2 power units for the power.
PUs.
And then they have IB switches, because they
InfiniBand, of course.
InfiniBand switches. There is 224 of those.
Yeah, you don't want to know how much that costs.
So this is basically being given away because somebody wants to get
rid of that, so they can install something new.
They can install something new.
Yeah. Okay. One other thing that we absolutely need to mention about Sandy Bridge, new process technology. So they went to 42 nanometers for that. It used to be 45, before that it was 65. So that was also a part of the reason why the next generation after Nehalem was quite a bit better. It was something like 20% faster, easily out of the box. I remember those tests. I still have the results somewhere on my hard drive on my NAS. I remember the impressions I got out of those systems. They were quite a bit more, let's say, speedy than what the previous generations were. You want to add something, or are we going to the next gen?
Next gen.
Next gen is Ivy Bridge.
Oh, Ivy Bridge was when things started to get interesting.
Yes.
And one of the reasons is because this was the first one when I would say lost interest in what is new. And the reason is that this is when I think they started to get boring. They just kept doing incremental updates that weren't that groundbreaking.
I would agree with the next generation, but not with this
one.
No,
I would say that this was the last one that actually had something new.
Okay, yeah.
And this was when the things started to get boring. We didn't know it way back then, but everything after this was just incremental.
Meh.
And I would call it meh, or just, okay, yet another generation. Yes, okay, fine.
Okay.
And then a new year, a new generation, let's see what is happening.
For the most part, up till 12th or 1st gen, I'm with you. Yeah, because
Okay.
most things that happen meanwhile for the next decade basically was small incremental upgrades, and as we are going to discuss later on, they had quite a few problems with the technology as well, with the manufacturing process. So Ivy Bridge was switched to 22 nanometers, and they started working with tri-gate transistors there. So that was a big shift. It's quite a bit more density. There, these transistors are much more energy efficient. They are much better at one of the fundamental problems of transistors, which is current leakage. And that meant quite a substantial shift to the better for the power consumption for the CPUs, which was back then and still is, and even more so in the future, very important for what we are discussing, as described by the example of this Cheyenne supercomputer being sold because it's inefficient by today's standards. Second thing that was quite a big shift, Intel actually worked quite heavily on the integrated graphics. This is when they introduced the HD 4000, I think, which was quite a big, let's say, improvement in terms of performance for the built-in graphics when compared to the previous generations.
It's because the previous generation had the HD 3000, the Sandy Bridge.
Yeah.
And the Sandy Bridge HD 3000 was basically an excuse to have a graphics.
Yeah.
It was more or less something that you would expect on a server. Something that is capable of displaying characters.
The Matrox
yes.
Of the graphics in that era, not before. Matrox before was, yes. PCI Express 3. That was the first generation that supported PCI Express 3.
And this was what actually was needed because you needed to have the graphic cards.
Yeah.
And the graphic cards
Bandwidth.
needed bandwidth because in order to have 3D, you needed to have high bandwidth communication with the processor and the rest of the system. And the only way to do it was to have chips supporting some way of talking to everything else, so periphery had to be upgraded.
Excellent point, to which I have two additional information for you. One, I just read an article today, actually.
Yes.
It came out yesterday. Don't remember who is the author. Sorry to not remember that. But basically, what the text, what the article is saying is that for the past 2 years, we had PCI Express 5, which is correct, and we are still not using it at all, which is almost absolutely correct. There are a couple of SSDs in PCI Express 5 that came out, but not an awful lot of them, and mostly nothing else for PCI Express 5. So that's the first piece of information, which I find curious. The second one, I already saw announcements. Actually, we saw it a couple of years ago, and last year and this year. But I saw an announcement that PCI Express 6 is already heavily being touted because that's what the industry needs. The fundamental problem, as we keep on explaining in our episodes, is the fact that the periphery and the way which we access the periphery from the application perspective, going through the CPU, through the controller, to the periphery and backwards, is super slow. And the faster we can get and the lower latency that we can get, the better the application performance is going to be. Even if we have the same CPU in the middle of that, it would still get quite a performance bump because of the bandwidth that potential future PCI Express cards could use, and or storage, of course, which is the key point of most of these technologies, as it's the slowest part of the system, storage being nothing more than another type of memory at the end of the day. So I find it very curious that the industry is moving towards PCI Express 6. I read some papers about PCI Express 7 already as well. And they're moving very quickly towards it without any real products being actually introduced to the market for it at all.
But I can see why. I see that one of the reasons is simply because they can. This is one of the things. Since they have already integrated everything inside the chip, it makes sense for them to just upgrade this part of the chip and say, okay, we are going to be able to handle higher bandwidth on the peripheral communication. And this is the same thing that is happening in the wireless community. The wireless standards, right now, Wi-Fi 7 is the current standard. And I don't know if there are any devices capable of doing Wi-Fi 7 other than a few phones, the latest generation phones, and other than a few, what you could probably consider test cards, because they are not cards that you would normally buy. I think that we have reached the point where we need to sort out the networking, and we need to sort out the periphery that needs that amount of bandwidth. So USB 3,
USB 4 now?
USB 4 or USB whatever needs to be sorted out in order to get the interface to whatever the storage is going to be. Because what we need right now is much faster storage and storage
and lower latency.
Lower latency and the storage that is not directly connected to your computer. This is much needed.
In the server market, that's the only way.
And the thing that we need basically is something that is going to switch over to what would we consider a network PC. The storage being somewhere else. We are calling it cloud storage and so on, but we lack the bandwidth and we have too much of a latency when it comes to storage.
There are two standards that aim to solve that problem that are very good. I worked with them. One of them is RoCE, which is based on Ethernet. Then the second one is NVMe over Fabric, which is for the most part based on fiber channel. Those are the next gen protocols being used for super fast, low latency storage access, and that's where the industry is going to go. I think the RoCE and the NVMe over Fabric, as it's called, basically DMA technologies, direct memory access technologies, are the next logical step. That's the only way because of the intricacies of the protocols that are happening between the server and the storage and backwards through the switch, cable, HBA, whatever. All of that is way too complicated and introduces a lot of latency. But with your previous point, you reminded me of something that's very important to mention as well. One of the problems and one of the reasons why we did a couple of episodes in the past, you remember we did a motherboard episode in which I ranted for 45 minutes about how I hate the current motherboard design for a variety of completely rational reasons. One of them being connectivity. And the fundamental part of that was the fact that both CPU manufacturers deliberately shrunk the PCI Express controllers on the CPUs in terms of the available lanes, which has a direct influence on the amount of cards that you can put on a desktop, specifically motherboard. They kind of went with the design pattern of desktop, you don't need additional cards. Servers, if you want to have a lot of PCI Express lanes, go with the server. And then you have the Epics of the world, the Romes of Milans of the world on AMD side and whatnot. And you can have your, 6 or 7, depending on the server, or 10, 11 if you have a 4U server, additional PCI Express cards. This is going to come to haunt them, actually, because of all of the things that we need in computers nowadays. We need a graphic card. Graphic card is this big nowadays. If you want, even in mid-range ones are super thick already. They're not just one single slot. I'm talking about the height of the
yes, I know, but
I'm being very...
Yes, you're being awfully cautious. We are talking about 3 slots wide,
at least.
3 slots high.
For something that's a little bit more than a mid-range
and
card.
You also need additional slot because you need somewhere for this air to go through. So you need additional slot above the card. So normal case has 6 slots. So you'll need 4 of those in order to get the graphic cards.
Which means that you're left with at most 2, maybe 3 cards to put in a normal case, which means that either they start manufacturing AA or ATX motherboards of the future, with much bigger dimensions or something to get us more cards, or they just keep on ignoring us like they do. I'm guessing that they're going to keep on ignoring us. That's the reason why I ranted so much on this episode.
And you're rating right now?
And I am right now, and I'm reminding about it because it is one of our most popular episodes because people agree, obviously.
I would just say a few things. First, you don't only need a video card. Today, I would argue that one of the things that you need more is a decent network card.
Yep.
We have come to a point where Intel is pushing for 2.5G networking, which is fine on paper, but it doesn't make sense in any other way or form. The reasons being basically that you can buy much cheaper hardware that is 10G.
Yes.
Simply because you have a lot of hardware that came from the server market. Server market has been enjoying 10G network speeds for the last 7-8 years.
More,
and you can buy a decent network card for something like €50.
Intel's cards,
used.
The Intel's two slot cards are around €100.
No,
X340.
no, they're not. X540 is right now can be bought for 50.
Well, I'm going to buy a whole bunch of them. Then.
Yes, if we are talking about the SFP Plus,
I'm talking about the copper ones.
Okay. The copper is a little bit more expensive, but the prices have come so low that you need a network card that is 10G. Even if you are just directly connecting...
Still €50.
Okay.
There's a whole bunch of them, actually.
And this is the reason that the market has been overflowing with hardware that used to be enterprise-level hardware, and that is now something that is cheaper than what you would pay for a single connector way back then.
Yeah.
And
that makes an awful lot of sense.
So you need to have additional network card. You are going to get much better speeds. You're going to get
offloaded performance.
You are going to get offloaded performance, and you're going to get much more stable network because the latency is going to be lower. The CPU doesn't need to do anything when it comes to server cards. So and also
the drivers are bulletproof.
Drivers are bulletproof if they exist.
That's why I'm mentioning it.
This is the only downside. And the reason is that Intel has decided not to release the desktop operating system drivers for some of the cards. So you need to...
These do have it.
Yes, but you need to check. Please, if you are following our advice on buying a card, you can buy cheap cards for 10G, but please check if the drivers exist for the desktop operating systems.
Yeah.
If the server operating system is supported, it is not a sign that the desktop is going to be supported. Make sure that your card is supported.
Yeah.
On the other hand, once you buy this card, you are going to be probably investing much more in your home infrastructure in order to get the Cat 6 or the Cat 7 networking. So this is going to be more expensive. And the switches themselves can be bought for $120 to $140 on AliExpress and different sites. I wouldn't call them actually good switches.
No.
But they are working. And people...
Netgears are starting point for that, and they're quite good.
Yes, but if you invest a little bit more, because you need to, for 200 something euros, you can get a decent switch. That is going to be 4 ports. But it is going to work, and you are going to end up with a much better network on your home side. And so you can finally move the storage away from your computer, and you can create a computer that is much quieter than what you usually have.
You are completely on the money, and you just reminded me of something. When I was assembling my last computer, 3900K, one of the things that I wanted to do, one of the reasons why I looked into those workstation motherboards is exactly that, because they have 10G, some of them, not all of them. Because I wanted to have 10G, reasons are completely understandable. We produce large video files from recording these episodes. I want to store them on my NAS when I'm done with the episodes. 10G for me, instead of 1G, means roughly, let's say, 5 times, 6 times in practice. 5 to 6 times faster transfer speed to my NAS. So I didn't do that, but I am going to probably do it in the future, or I'm just going to move my NAS to be closer to my computer, direct connected, and bye-bye. Because that's actually a worthwhile investment for us, as we are time pressed for
this is worthwhile investment for everybody. Yeah. Since you can, if you go that way, and we should do another episode on this.
We should.
When you go another way, you need to understand that you are going to be running into bottlenecks all the way.
Yeah.
You are going to be having bottlenecks where you don't expect them. Your NAS is going to be too slow. Mm-hmm. Suddenly, you're going to realize that you are able to saturate your NAS just by copying a file of it. And if we are talking about Synology or something like this, usually you can get away if you have a single user and single device accessing the NAS. You can get away with 10G. Some of the Synologies, the ones that have this PCI Express slot, can even be upgraded to 10G.
Yes.
So you can get a pretty cheap NAS and then upgrade it. But I would call it's much easier nowadays to just buy an older Gen 9, Gen 8 but I would use Gen 9 server,
HP.
and then put, I don't know, 5 or 6 disks into it, and then just create a NAS that is going to be much faster.
I agree, because those Gen 8, Gen 9s, I looked into it last week, and we bought at least one a couple of months ago for the backup, for the new server, because it's fast enough. I don't need anything faster. We got one of the Gen 9s with 128 gigabytes of memory, 32 cores for 240 euros.
Yes, I know.
And you can put, those are the 2 to 2.5 inch models. Those can have
12,
up to 16.
12 to 16.
Up to 16 disks. I mean, just start putting terabyte drives in. They're not as expensive anymore. If you're some kind of SMB, that's a winning strategy. I prefer OS Nexus. He likes Unraid or something.
I would go, and right now, if I'm talking about this, I would just go with straight ZFS. If I'm able to, if I'm able just to have only this, so only storage on the server, Linux ZFS, let it use the entirety of the 128 gigabytes of RAM for the cache or for the log. Do the zlog on this on the NVMe disk, and you are completely foolproof when it comes to being able to actually push gigabyte over the network, and being able to actually use the disk as if it were at your on desktop.
We wrote 3 papers about this in the past 3 or 4 years, and I'm preparing a journal paper about this for HPC market right now as we speak. I'm finishing one. This is an incredibly potent software combination for the stuff that we discussed. But back to the topic at hand. So we talked about Ivy Bridge. Next one is Haswell, 4th generation Intel Core processors. They somewhat improved the free gate transistors technology that they were using to produce the previous generation. They introduced some kind of a new voltage regulator, which was much more capable in handling the power end to deliver a little bit more efficiency.
Let me stop you there. The point of the voltage regulator in Haswell was not that it was more efficient. The idea was that they took the role of the voltage regulator to the chip, not on from the motherboard. And the idea was that they were trying to make the motherboards that are more stable. If you way back then, if you were betting on the motherboard to be able to regulate the voltage, sometimes the cheaper motherboards were unstable simply because the voltage was unstable.
Oh, I remember those motherboards well.
Yes, so this is the point when cheaper motherboards and much more expensive motherboards came much more close to each other, simply because the stability was there. So I think that the probably the integrated voltage regulator, or FIVR, or as it was called, is one of those things that made sense much more than people actually thought it at the time.
Yeah, I looked at that as a, I wouldn't say marketing, more technological gimmick when I was testing it. I remember it now. You helped me recall some memories, but you're completely correct. I was way back then, just to kind of like get it out of the way. I think I was kind of spoiled by the high-end motherboards that I was getting that had, 4-phase power delivery, which was done with the super strong and very expensive Japanese capacitors. I used to have a lot of gigabytes motherboards that were made that way. They never failed. Never, ever, ever, ever failed. And I still have some of them actually in my computers that I'm using till this day. They work like crazy.
But the thing is that this is the reason why I'm always trying to use the lowest and the cheapest possible technology when it comes to something, because I'm going to see the problems first there. If somebody is chipping out on capacitors or chipping out on voltage regulators and so on, you're going to notice it on the cheapest possible hardware.
Yeah.
If you're using the high-end hardware, they usually get rid of all the problems, so you are not going to see the problems that are inherent for the motherboard and that are not part of the CPU. If a CPU is stable on the high-end motherboard but is not stable on the cheap motherboard, this means that the CPU is okay, but the motherboards have a problem.
I have a working system from this generation. It's in our office, the silver Cosmos case. It has a gigabyte motherboard and Intel sample CPU. It still works to this day. That's 11, 12 years later, works no problem. And it just goes to show you how those engineering samples that were done way back then, how over-engineered they were on both sides, both on the CPU side that were usually specially binned, and on the motherboard side, because that motherboard is unbreakable. It's just incredible. I've never had a motherboard like that, which, you could do anything you want with it, it still works. Unbelievable.
I'm just going to go with the one thing. I wanted to say that this, when it comes to numbering, we need to establish something. We're talking about Hassel's, we're talking about different versions of the processors. Hassel's were the 4th generation, i5 4, i7 4, and so on. And I have more than one of those still running.
Yes, I know.
On Asus motherboards, and they are completely capable of doing, I would say, almost everything that you need day to day. They are unable to keep up with, I don't know, 4K rendering. But if it comes to normal working, using the internet, doing some light media production, and basically everything other than heavy lifting when it comes to video.
Perfectly capable.
4790 is completely capable of doing it.
Yeah, you got me a couple of those systems. Yeah, they work perfectly.
Because I had those for different reasons. Also, we need to mention that this was the I just got remembered by my script. This was when they introduced the HEDT, high-end desktop idea,
which they left afterwards and came back.
So 4960X. What was then the Extreme segment. Before it was called just the Intel Extreme. So the Extreme segment was something that later became i9, give or take a few. Give or take a few components. It was the 6-core and 12 threads processor designed for high-performance tasks like video editing, 3D rendering, and gaming. So these were the processors that can hold up to modern processors when it comes to usability. And we are talking about processors that came out, 10 years ago?
Yeah, easily 10 years ago, which is still incredible. One more addition to the Haswell generation, very important additions. Some AVX and FMA instructions were added as separate registers to speed up some of the processes. We already talked about AVX previously, so nothing new to add there. FMA is multiple addition methodology, if I remember correctly. These were something like 10% faster than the previous generations. I remember from the tests that I did, which, tick-tock strategy, which we can discuss in some future episodes. Yeah, and they were... Actually, I remember that we had a test in which we were testing more towards energy efficiency. Again, they were quite a substantial bump compared to the previous generation. They also introduced the HD graphics for the 600, I think it was, which was something like 30-40% faster than the generation before that. Quite a substantial bump.
The one thing that I actually need to do some research on is, why do I see so many systems on the market? I'm talking about the refurbished market that are basically Haswells. Why are so many laptops available right now on the cheap i5 4 somethings?
Might have an idea. You might have some.
I don't have an idea, because I would suspect that you would probably need, or you will probably see newer models and older models. Everything that I see right now on the market is either the Haswell or sometimes brought the next generation. But usually it's Haswell.
Yeah, I have a very good idea why. And you actually answered to your question to yourself 5 minutes ago. Because those chips were so good and they withstood the test of time so well that if you take a laptop with the CPU of that generation, just stick a freaking SSD in, you're happy. Most of the market doesn't need anything more. So that's the technology perspective, and the price perspective, because they're super cheap.
Yes, as you saw, I sent you prices of the used laptops of that generation. Right now, they are under 200 euros.
Yeah, and correct me if I'm wrong, but though again, those CPUs, those generations of the CPUs and the corresponding systems like this one, I have at least one of those systems in Lenovo laptop, are more than enough for vast majority of the market to do any kind of business in and all of the stuff that you mentioned. As long as you have SSD, no problem whatsoever.
So as they will say with the pets, don't buy, adopt. Get an older one and get an older laptop. Don't buy a new one. Don't buy a new one.
Yeah, that's good. Okay, so Broadwell.
Yes,
next
Broadwell.
generation. So that's 2014-15 time frame. They switched to 14 nanometer with Broadwell. Again, introduced new integrated graphics, which was again something like 30% faster. In the laptops, that meant quite a bit more efficiency, which again meant less power consumption or longer battery life. And with that came quite a bit of, let's say, additional bumps in terms of the performance and whatnot. But this is not the generation that I remember all that well for some kind of exclusive desktop. Something I remember them more from some other, let's say, parts of the market. I saw some, if I remember correctly, that's the generation that a lot of people used for SFFs, small format PCs and whatnot.
I would say that I wasn't seeing, or right now I'm not seeing a lot of those systems on the market, or I haven't put together while I was working in this particular field, since this was still the time when I was working as a guy who was doing not only the DevOps part, but also the manual part of putting together a PC. I wouldn't say that I got too many systems based on those chips. Yeah. For some reason, Skylake, the next one, was prevalent.
Completely different.
Yes, but it was prevalent. Either it was the generation that was before, so the Haswell. Mm-hmm. Or it was the Skylake. I didn't say anything in the between.
Yeah, there's a reason why. Because the Broadwell wasn't the desktop CPU architecture almost at all. They only had like 4 or 5 CPU, 2 initially, and then 3 or 4 more afterwards in the i5-6 generation that were Broadwell based, Broadwell E, and all of the other CPUs were exclusively for the mobile market.
Yes, and
there are a couple of embedded ones, but nobody cares.
But the thing is that when I was saying that everything after the Ivy Bridge was boring, the reason why I say this is that when you take a look at all the different things that what were the key features of a given architecture, mm-hmm. You're going to see it improved, and then whatever. Improved graphics, improved architecture, improved memory support, improved power efficiency, improved platform support, and mm-hmm. so on. But everything is just improved. Mm-hmm. There are no big changes. Mm-hmm. I can understand that when you are switching the process, if you are switching the size of the die and so on, you are going to have some developments that are going to happen simply because you are switching the size of the die. Mm-hmm. If the processor is smaller, it's going to be using much less energy and so on. So when somebody says to me, okay, we have better performance, of course you have. You wouldn't be releasing a new processor if you didn't have any better performance. Okay, this has also happened.
It has.
Yes, so this is one of those things when you cannot be sure completely. But then again, I'm not, especially when it comes to Skylake, I'm not that, people say that it was a significant step forward.
It was. But we're not talking about Skylake yet. We're going to. There's one more thing to add to Broadwell's story.
Which one?
So most of the CPUs were mobile CPUs. The U CPUs were very popular back then. There's one other part of that story that's super important. This was the appearance of Xeon Ds.
Oh, okay.
And that's actually important.
That is
because that meant that Intel, basically for the first time in maybe even forever, was able to produce small box servers. You know, my Supermicro, and there are many of those, like NAS case-based, let's say, smaller servers for small, medium enterprises if they wanted to, which were really small in size with decent performance. I remember I have a Supermicro SYS version of that, which is Xeon D1541. I still have it till this day with boatloads of memory and NVMe SSDs, ESXi running on top of it, working beautifully. So Xeon Ds were actually very important because that helped Intel branch into the SoC market. Specifically, the reason why that is important is because those CPUs ended up in not only these small servers, but in NASes, in Synologies, in QNAPs, in all of the other stuff that was related to, let's say, SME SOHO business for storage part of the market, not only for the servers. And they were very popular there.
And the thing that is most
and then Ethernet support.
the most ironic part of all of this is that when you mention the configuration and everything else, the only thing that is out of date and that is end of life is the SXI.
Yeah. Yeah, from that list, because that small box is still sitting at home with me. We had it in the office for years. In our data center, we used it for our internal, playing around with virtual machines, preparing them for classes. It still works very well. I have an Intel 750 SSD inside, PCI Express one. Everything that I need to do and test, I can do it easily with those. It's my equivalent of doing NUC-based systems nowadays, because it's very small, very efficient, 8 cores, 256 gigabytes of memory, something like that, 2 SSDs, nothing you can do on those. So you can do everything you want to on those. And finally, we are getting to Skylake, which you mentioned. Again, improved process, 40 nanometers. Much better GPU performance. We're talking HD Graphics 5 series now. These were the first CPUs that supported DDR4 as well, so which is a significant shift. Quite a few new additional security features when introduced, whatnot. But my prevalent, let's say, memory of the Skylake was actually that it was quite popular on the desktops, unlike Broadwell, which was non-existent.
Yes.
On the desktops. I remember vividly testing some of those systems as well. I don't know if you had any of those on your desks in various side jobs that you used to do, but maybe you have some stories about that too.
Yes, but I would say that I had the most of the desktops that I saw in production would probably be the ones that were after the Skywell. So Skylake, sorry, either the Kaby Lake or the next one.
Mm-hmm.
So I would just say that this was okay. Let's do a personal story on this, because I have opinions when it comes to process of these years. The thing that changed, particularly, we're talking about 2015, 2016.
Actually, for quite a few years to come, Skylake X, Skylake E, Skylake this, Skylake that.
What happened is that most of the people stopped counting.
Yes.
And the reason being that you had a processor that is completely capable of doing everything that you wanted to do. Yes. For most of the people, the processors that came 10 years ago are completely capable of what they need. They want to be able to go on YouTube. Fine. Mm-hmm. Given enough memory, they can do...
An SSD.
Given enough memory, they can do everything that they want to, and they don't need to invent anything. So a lot of those processors are still alive, if and only if they chose the right motherboards.
To your point, the laptop that we used for one of the Red Hat classes a couple of weeks ago, which has 2 NVMe slots in, a Lenovo laptop that you have, which CPU does it have inside? Which gen?
Honestly, don't know. 6 or 8.
I think it's a Skylake. I'm not sure.
It probably it is. It's a P50, but I don't know what the. I'm right now just waiting. The reason why you got the refurbished list is because I'm constantly polling the guy who is importing the refurbished laptops, because I'm trying to get the P51 or P52 on the chip. Right now, the P51 is probably the cheapest.
Not on the chip, on the cheap.
On the chip, yes. I'm trying to get the least expensive workstation that I can get my hands on, because I think that P50 was probably the last Lenovo workstation that was so expandable as it was. 3 disks and everything else. After this, you had to just use NVMe's. but also P51 and P52 are the workstations that I would like to have. I would like to have at least one of those.
Okay.
And we are talking about the workstations that are probably around 300 euros right now.
Yeah, and still 8 or 9 years old.
Yes, and also
Quite capable of doing anything we need.
And also, if you want to buy the charger by itself,
it's more expensive than the laptop.
It's not going to be more expensive, but it's going to be half the price of the entire product.
Okay, I can counter that. If you want to buy a docking station for that, it's going to be more expensive than the laptop.
Yes, but the thing is that right now it's cheaper to buy any Lenovo older laptop with the charger than buying the charger by itself.
Yeah, economically, it's not viable to just buy the charger. It's much more efficient to buy another laptop with the charger. I agree with you.
Which is stupid.
Which, yeah, all in itself is definitely stupid. The Skylake part of the history, actually, this is where my interest began to show a little bit back towards my journalistic side, where I started reading about it a little bit, but not nearly as I used to. And the reason why that interest faded very quickly is easy to explain. The amount of Skylake types of CPUs that Intel made in the next couple of years. So first they had the original Skylake, which was 6 series. Then they had high-end desktop Skylake X, which was 7 series. Then they said that the 9th generation Skylake X high-end CPUs were 9999X, 9990XC and whatnot CPUs. Then on Xeons, they had workstation CPUs. Then on mobile, it spanned Series 6, loads of CPUs, various different types of Xeon Ws that started with, for example, number 2, then with number 1. Then they went to Xeon Silver, which was Xeon Bronze, which was Skylake SP, scalable. And I'm actually looking through Intel's page for this, and I'm not yet done. That's why it became so boring so quickly.
I'm going to stop you, and I'm just going to tell you that you need to get this page on the screen and just let it slowly scroll.
So the page speak the words that I say.
Yes, so that we don't need to mention all of these.
This is where they started getting in a heavy rut.
Technologically, this is when they decided that they have good enough technology, and now is the time to monetize it. So they decided that they're going to be stopping, not stopping, but they're going to be slowing down the advancements because nobody needs them. And to be fair, at this particular point in time, nobody was needing it.
To be fair.
And so they were right on this part, but they pushed this idea too far. Nobody was needing a small upgrading technology, but everybody was waiting for the big upgrading technology.
Yeah.
And
for the next 5 generations that didn't happen.
Yes, you can call me on it, but I think that the next big thing that happened in technology after the Skylake was AMD.
Agreed.
They completely shook the market when they introduced the new
Ryzens and whatnot.
The new Ryzens, yes.
Okay.
But this is much later.
Yeah.
It's not much later. It's
not
4
much.
years later.
Not much, yeah. In terms of what we were living through in those 3 or 4 years until that happened was the list that I just gave you, basically.
So, Kaby Lake.
No.
Okay.
Hour 12.
No. Let me just.
No. It's a second episode.
But let me just say what Kaby Lake was.
No.
Enhanced process, enhanced clock speeds, improved graphics, faster memory, native support for USB 3.1, and optimized video handling.
And with that, that's where we end, and then continue talking about it in the next episode.
Yes.
That's a precursor to the next episode.
So this has been the episode on the how Intel came from
Core 1,
how Intel came from the hole of that they themselves dug themselves in with the single core processor, and they introduced a plethora of architectures that were Some were sometimes boring, sometimes interesting, but they pointed towards multi-core computing, and they defined some of the things that then different vendors were able to implement correctly. Thank you for being with us. Thank you. This is Vedran. I'm Yasmin. Bye.